In the last video, we created the fourth degree Newton interpolating polynomial, and then we used it to approximate some values in between the given values of x for our Bessel function. Right? So now what we're going to do is we're going to go ahead and we're going to determine how good are our approximations. In other words, what error is there? And then also, if we were to plot it on the same graph as Bessel, does it look like it belongs there, or is it kind of just all over the place? So relative to the error, how close are we? All right, so let's start by finding the actual values and then the percent error, and we're going to print those in a table. All right, so first thing we're going to do is let's get our actual, and the actual is going to be equal to, we have our function Bessel J of the first kind, all right, and then that's going to be equal to, we're just going to substitute these x values in. Okay, so these are the x2s. Now we're going to find some errors. So I'm going to do a for loop for this. So for I equals 1 colon length of x2, I'm going to say error I, I'm just going to call it error I, is going to be equal to the absolute value of y2. All right, and remember, y2 is the approximated value. Okay, so this is going to be y2i minus actual I. All right, and then we're going to divide that by actual I. And we're going to multiply that by 100. All right, so that's going to be our errors. All right, and let's end this. All right, now let's go ahead and in our table, we're supposed to print this out. So we're going to find the, we're going to go ahead and print out the x value, the approximate, which is going to be f4 at x, the actual value, which is Bessel at that value, and then we're going to print the percent error. All right, so let's have a header here. So we're going to have f print f, and we're going to have the x value, and then we're going to have f4 at x, and then we're going to have j1 at x, which is the actual, and then we're going to have p error. Okay, so our percent error. Right, and let's just have a for loop. So for I equals 1 to the length of x2, we are going to f print f. So we're going to start with x2i, right? So that's going to be, now remember, we could just say that's percent 2.1 f. And then we're going to have our f4, which is the approximation, right? So that's actually y2 right here. That's going to be percent f. And then another percent f, which is going to be the actual value. And then finally, we're going to have the percent error, which is yet another percent f, right? And then we're going to enter. Right? So that's going to be x2 at I, and then y2 at I, and then the actual I, and then finally we have this error I. If I was smart, I would have just done the error in the same for loop, but I guess I'm not all that smart, and we're going to end. All right, so it might not line up, but let's see what we get here. All right, so I'm going to just space this out a little bit, but the initial results look pretty good here. All right, so run it. All right, and maybe p error. All right, and just for my sake, I'm going to go ahead and just do one more enter here, just to make it look a little aesthetically pleasing. All right, so here's what we get. So this is the x given, and that's the values in between. That's the interpolated values. This is the value of the fourth degree Newton interpolating polynomial. This is the actual Bessel value. All right, and notice how close these are. So close. In fact, the percent error is 0.003%, not 0.003, but 0.003%. In fact, the highest percentage we get, and that's expected as we get further away from the beginning of the polynomial, we have a little bit more error in that sensitivity of that fourth degree is going to be 0.0629%. All right, so that's a really, really good approximation. So if all goes to plan, when we graph this, this should be exactly almost on the Bessel curve. All right, and for our last part of this, we're asked to be able to plot two functions, or two plots, excuse me. We're going to plot the Bessel function from 1.8 to 2.6, and then we're going to plot our coordinates on the same graph, and then we're just going to change the span from 0 to 30, so that way we can kind of get an idea of what the Bessel function looks like. All right, so let's get to it. So I'm going to define x4 to be another variable. And let's say x4 is going to be equal to the vector or the row vector from, I think we said from 1.8 to 2.6, right? And let's let y4 be equal to Bessel J of the first kind at x4. And what we're going to do is we're going to do a subplot. So this is subplot of 1, 2, 1. And let's plot x4 versus y4. So this is the actual function. All right, so this is the true Bessel function right here. Now we're going to hold on, and we're going to plot, if we go back up here, x2 versus y2. Those are the estimated. So x2, y2, and not feeling too froggy, so I'm just going to go ahead and use the circle. We can hold off, and I'm just going to title this. So I'm going to title this the Bessel, and for interpolations, using f4 of x. All right, so, and we could do the other ones. And now what I'm going to do is I'm just going to go ahead and do the exact same thing, except I'm going to change x4 and y4 to, I believe we said 0 to 30. And I'm just going to make this a 2, and I'm going to say Bessel over 0 to 30. And the 4, and I'll just say Bessel over, I think it was 1.8 to 2.6. Okay, now this will be more of a zoom, and then this is going to be the larger plot, so that way we can kind of get an idea of what the whole Bessel function looks like. All right, so let's give it a run, see what happens. Excited. Hopefully there's no syntax errors as to kill my excitement. All right, so we get a figure. All right, cool. Okay, so here are, and this is a pretty good zoom. Okay, so this is an approximation or interpolation. This is an interpolation, this is an interpolation, this is an interpolation. Notice this one, and if you zoom in, you can see that it's almost dead in the middle of the curve because there was almost no error. And then as we start getting a little bit further, it starts going just a little bit off that curve, all right, but not too terribly, all right? So in fact, the interpolations are all really good for Bessel, all right? Now, this is a picture of what the Bessel function looks like in its entirety, okay? And as you can imagine, it's almost like a damped sound wave, okay? So for instance, if you shoot a gun, if you're really close to it, you're going to hear it, okay? But over time, that sound wave starts to dissipate a little bit, all right? So it's almost like a damp sort of thing. With the Bessel function, though, it never really goes to 0, okay? So if you really wanted to, for those of you that have never seen a Bessel function before, I can go ahead and change this to 100 just for curiosity and run it. And then this will change. And so notice with the Bessel function, it eventually, you know, it doesn't really shrink down too quickly, all right? Like eventually, like a damped sine function or something like that will eventually tend towards 0. In fact, if I really wanted to, just for those of you that care, I can put in 1,000, to see what the Bessel looks like. That's pretty cool. And so notice like these oscillations get really, really close to one another. It almost looks like a volume of revolution from Calc 2, but you probably wouldn't want to use a Bessel function anywhere in Calc 2. Even, by the way, a Bessel function is convergent, by the way, using a ratio test for those of you that ever wanted to use that. So pretty cool, all right? The whole point of this is to be able to take something, and I'm going to return back to what a Bessel function is, all right? A Bessel function is pretty tough to compute, all right? So one of these guys to compute by hand to find the value is really tough. So if we were to even use a 6th degree interpolating polynomial, that could probably get us really, really, really close instead of just really close, all right? So hopefully that helps you to understand the importance of an interpolating polynomial. And if we were to use something pretty complex like a Bessel function, that we can use that interpolating polynomial just a 4th degree to model that thing. Now, in the next videos, we're going to look at a secondary type of interpolating polynomial. This was the Newton interpolating. We're going to take a look next at the Lagrange interpolating polynomial. So hold on tight. It's going to be a fun ride.